Okay, let's do this example from Kundu and Cohen where we must do a mass and momentum balance for a control volume of length ds, and it is given that the control volume is a stream tube. So a stream tube consists of many streamlines. So in a flow, if so let's say these streamlines, there is no flux which intersects them, and if they form the surface of a tube, it's like a bundle of streamlines which originates. Okay, so the flow which enters a stream tube always remains bounded inside a stream tube. Okay, so let's see if I can draw this in a better way. So let's say this is the entry. So all these lines are the streamlines, and fluid remains bounded inside the locus of all the streamlines, sort of. Okay, so this surface is called as the stream tube. Okay, so in a stream tube of length ds, we have to obtain the Bernoulli equation along a streamline. So in general a streamline can be curved. Okay, this is the s direction, so s represents the direction along the streamline. This is the location 1, and let's say this is the location 2. Okay, here the velocity is always normal to the face of the stream tube, so this is u. The n vector for this face is here, n vector for this face is over here. Okay, so now let's first do conservation of mass. So we choose a control volume which does not move. Okay, so this is our control volume. So control volume is fixed, b equal to 0. So we have tdt of integral rho dv plus integral rho u minus p dot n dA equal to 0. Because the flow is steady, we have this term vanishing. So essentially, upon setting b equal to 0, we have integral rho u dot n dA is equal to 0. So this is essentially giving us so velocity here is gonna be u at s plus delta s. The area here is going to be s, the area of s plus delta s. This whole length is ds. Okay, so this integral at the left face is rho u dA, minus sign because u dot n cap will be minus 1, plus on the right face rho, so this area will be a, this will be a at s plus delta s u dA. So this u will be at s plus delta s, and because there is no viscosity and if the area is small, we can assume that the velocity profile is constant, and therefore rho u a plus rho u s plus delta s times as plus delta s equal to 0. Therefore, rho ua is equal to rho u plus del u del s delta s times a plus del a del s delta s. Okay, so this equation we call as equation 1. Conservation of momentum. Okay, so on the left hand side we have ddt of rho u dv plus rho u minus b dot n dA is equal to summation of all the forces. And because it is given that the flow is inviscid, the contribution of force only comes through the means of pressure. Okay, contribution of force only comes to the means of pressure. It is given that it is steady, inviscid, constant density. Okay, that's why we choose rho equal to constant over here. Otherwise, this rho will also have a rho plus del rho by del s delta s component, which we needed to account for later on. Okay. So given that the flow is steady, this term will vanish. So then we have integral rho u dot n dA is equal to summation of f. Okay, so on the left face, we have rho u a. This whole term will become this. On the right face, it will be rho u at s plus delta s, u at s plus delta s multiplied by a at s plus delta s. Okay. Now this will be equal to summation of f. We'll come to what summation of f will be. So let's expand this for now. So LHS minus rho u square a plus rho u plus del u del s ds square a plus del a del s ds. This is also equal to, now let's make use of this rho u plus del u del s delta s times a plus del a del s delta s. So rho del u del s delta s, so one of the power comes from here, and this becomes minus rho u square a plus rho u a multiplied by u plus del u del s ds. Okay, so this power is actually two terms, so if I want to, I can write it as this. The square I split in two terms, and this term, this whole term, is nothing but the right hand side of equation 1. We substitute over here. So this term becomes equal to minus rho u a u minus del u del s delta s is equal to rho u a del u del s delta s. So what are the summation of forces acting on the system? Okay, the next question is, what are the summation of all the forces acting on the system? So let's copy this, let's paste it over here. Okay, so for an inviscid flow, there is no effect of stress because stress depends on viscosity. Okay, and for this kind of flow, which is inviscid, the only contribution comes through the Euler equation, so the pressure. Okay, so here the pressure is P, just pointing normal to the face of the area, and here the pressure will be P at S plus delta S. Okay, but the fact of the matter is this direction ds is gradually varying. So if this angle is theta, the pressure here will be like this, and it is varying up until his. So there are forces acting on the normal faces, which are P and this. So these are normal faces, and these are the forces acting on the conical faces, on the curved surfaces. Okay, and if this whole tube is inclined at an angle theta, then the mass of this whole element, if this is mg, so the component in the s direction will be something like this. Okay, so that will be equal to minus rho g sine theta. Okay, so this force along, okay, anyway, so let's write this down completely. So it will be P into A acting in the S direction. So summation of force will be the contribution from the surface force first minus P plus del P del S ds multiplied by A plus del A del S delta S. So these are the contributions from the normal faces. So the second term will be the contribution from the curved surface. So let's write that down as P curved times A curved, and the last term will be the effect of gravity. Okay, so the effect of gravity is equal to the volume. So what is the volume? It's equal to ds multiplied by A plus the average area. So A plus del A del S ds by 2 multiplied by rho multiplied by g, now the component. Okay, so if angle is theta, so this will be 90 minus theta, so minus volume times sine theta. Okay, so now let us try to imagine what P curved times A curved will be. Okay, so say this is the curved surface. Okay, so at any, so this will be like the, so this pressure on the curved surface is acting normal to the surface. It is not acting on this area, but rather on the periphery. Okay, so what is the peripheral area? So if this direction, let us say we call it x, then the pressure at any distance, so if the pressure here was P, like on this face, the pressure at any location will be simply P plus del P del X dx. So here it's not dx but P plus del P del X multiplied by x, because this area is located at the location x. Okay, so the area at this location is what? So the area of periphery. So this whatever this pressure is acting on the difference of the area. So here, for example, there is no difference, but here if we project this area, we get this, and the oblique component of pressure is acting on this difference of area. Whatever the oblique component is, it is acting on this. Okay, so the difference in area will be del A del X times dx. Okay, so that will be equal to del A del X times dx. this is dx, this is x. So P is P plus del P del x times x, and the area on which it acts is del A del x times dx. So then let's see what the, so this is a df. So what is the f? F is equal to integral P plus del P del x x del A del x dx. So this goes from 0 to delta s. This will be P plus del P del x let's multiply this completely. P del A by del x dx plus del P del x del A del x x dx integral 0 to delta s. So this is equal to P del A del x delta s plus del P del x del A del x delta s square by 2. So this is equal to P plus del P del x del A del x times delta s by, oh my bad, so this is equal to P plus del P del x delta s by 2 multiplied by del A del x delta s. Okay, so this is PC into AC. Substitute this in this equation. Okay, so summation f summation f is then PA minus P plus del P del S ds A plus del P del S ds plus P plus del P del S ds by 2 times del A del S ds. Okay, so this is equal to, oh so we forgot this, minus rho g ds sin theta A plus del A del S ds by 2. Okay, so this will be equal to minus del P del S so minus del P del S times, so this is A, minus del P del S times then minus del A del S P times ds minus del P del S del A del S ds square. So this P into A we have cancelled from this, plus P del A del S ds plus del P del S del A del S ds square by 2 minus rho g ds sin theta A plus del A del S ds by 2. So this is equal to, so this term and this term also get cancelled, so minus del P del S ds A. So let's neglect all the terms involving delta s square, because in the end the limit is always ds tends to delta s tends to 0. So this term get cancelled, so this term only survives. So this term will be minus rho g ds sin theta into A. So this ds when multiplied by this del A del S ds will give it this ds square, which is then neglected. So this is equal to minus del P del S ds A minus rho g ds, so ds sin theta, what will be ds sin theta? So this was ds and this was theta, so clearly ds sin theta is equal to dz. Okay, so on the left hand side what did we have? the left hand side we had this rho UA del U del S ds. Rho UA del U del S ds. This is equal to minus del P del S ds A minus rho GA dz. Okay. So this term can be written as rho A del S of U square multiplied by half, because these two terms are equivalent. Convince yourself that these two are equivalent. Minus del P del S ds, so we forgot a ds over here, minus rho GA dz. So let's divide everything by A times ds. So we have rho del S U square by 2 is equal to minus del P del S minus G dz, which gives del P del S plus rho del S U square by 2 plus G dz equal to 0. So this dz divided by ds. Okay, so essentially del S P plus rho U square by 2 plus G Z is equal to 0. This is itself the Bernoulli equation, which we have derived using the mass and momentum balance for a stream tube. The main idea was that for a stream tube there is no flux through the side wall. By definition of a stream tube, there is no flux through these surfaces. Whatever flux comes in through this end has to go out through this end, and then you simply do a mass balance and a momentum balance. And the only tricky part was to find out the force acting on the curved surface. The curved surface force is found out using the pressure multiplied by the projected area. The projected area is the difference in the area, hence this del A del XO comes into picture. This, when you integrate over the entire curved surface, gives this kind of a pressure, and then you obtain the final solution. Okay. There are multiple ways of deriving the Bernoulli equation. This is the integral way of obtaining the Bernoulli equation. The integral way of obtaining the Bernoulli equation may not look the easiest, but it works. It follows from simple considerations of mass and momentum, and is actually a statement of the balance of energy in the end. But because there is no viscosity involved, it's also a statement of conservation of momentum and mass. Alright.